Good afternoon, everybody. Welcome to the IWF seminar of this week. Today, our speaker is a guest from China, Nihan Chen. She's at the moment trying to finish her PhD at Beihang University, and she basically works on Venus, as you can see here from the title. She's working pretty much on Venus. She has a couple of papers, one doing a multi-fluid Hall magnetodynamic study of Venus, as you can see here also in the title, but she's also looking at perpendicular parallel asymmetries of the Venus bow shock on the different Parker spiral directions, and she has which is under review at the moment, as paper, and another paper also on the review about solar-Venus interaction during solar maximum and minimum periods, and also doing a multi-fluid MHD model. Maybe part of that is also included in this talk, but we'll let ourselves be surprised. She'll be here. Her planned visit was for 6 months, and 1 month has passed now, approximately 1.5 months.
Actually, 2 months has passed.
A bit more. Okay, then I'm miscounting. I'm sorry. And we're very happy to have her here. It's not her first presentation in Austria, because she also had a talk at the EGU.
Yes.
In Vienna, so she knows now everything about how things work here in Austria, and we are very interested in what you're going to tell us about Venus and the magnetohydrodynamic model you're working with.
Now let's start. Good afternoon, everyone. My name is Nihan Chen, and I'm from the School of Space and Earth Sciences of Beihang University, and our university is in Beijing. Today, I'm going to talk about the solar wind interaction with Venus' upper atmosphere, and I will present some findings obtained through our Hall Multi-Fluid MHD model. And I'm very glad to have this chance to introduce my work to all of you in this room. And by the way, thank you, Daniel. I noticed that you are here. And our MHD model was entirely developed by our research team in Beijing. And besides Venus, we have also developed similar models for Moon, Mercury, and Mars. Okay, this part is our short research background. We all know that Earth has a very strong intrinsic magnetic field, or we call it a dipole magnetic field, to protect the Earth's atmosphere from the solar wind. And this protection can help Earth's atmosphere to be more stable. But things are completely different on Venus and Mars. For Venus, Venus does not have such a strong intrinsic magnetic field, so the solar wind can interact with the Venus atmosphere directly. And during this process, some atmosphere components were blown away by the solar wind, and we call it these components escape from Venus. And after the escape of some components, of remain greenhouse gases like CO2, the carbon dioxide, triggered a runaway greenhouse effect on Venus. As for Mars, Mars has some crustal magnetic field on its southern hemisphere, but this type of magnetic field is not strong to protect the whole atmosphere on Mars. So there is still some components of atmosphere escape into the universe or into the space. And finally, this less solar radiation and the escape of the atmosphere components leads to a runaway ice house effect on our Mars. So we can say that atmospheric escape is a key process in shaping the evolution of planetary atmospheres. But the atmosphere can escape in two main forms. That is, they can escape as neutrons or they can escape as ions. For neutral particle escape, they can escape through different processes like gas escape, photochemical escape, hydrodynamic outflow escape, or some sputtering process. Gas escape is a thermal process when particles in the upper atmosphere gain enough energy, then they can escape into the space. For photochemical escape, this type of escape is a non-thermal process. The photochemical reactions can create some energetic particles, and these energetic particles will escape into universe or space directly. And the hydrodynamic outflow, yes, we can say it from its name, it's a hydrodynamic process. And finally, as for the sputtering process, the sputtering process is also a non-thermal escape process. It happens when the energetic particles from the solar wind hit the atmosphere, then some neutrons will be knocked out into the space. As for ion escape is my research focus now. And the ion escape is totally different from the neutron escape because the ions are charged. And the ions comes from the ionization of the neutrons by solar photoionization. And once the ions are formed, they will become very sensitive to the electric field. And they will be accelerated by the electric field or some fields, and then join the solar wind flow. After joining the solar wind flow, they will slow down the solar wind, and the solar wind will continuously catching some ions, and the solar wind will bring these ions into space. So we can say that the ion escape is strongly influenced by the interaction process with the solar wind. There have been many missions regarding the solar wind interaction with Venus. For example, we have Pioneer Venus Orbiter, which was launched in 1978. It was quite a long time ago. And we have Venus Express, which was launched in 2005. As we said before, the Venus has no strong intrinsic or dipole magnetic field, but Venus still has some structures of magnetosphere. We call it the induced magnetosphere because it comes from the pileup of interplanetary magnetic field. The induced magnetosphere of Venus has been detected by our missions. Firstly, the solar wind will encounter a bow shock, and the bow shock can decelerate, compress, and heat the solar wind. And behind the bow shock, we have the magnetosheath, and the magnetosheath is a transition region, and this region is populated with the solar wind particles. And below the magnetosheath region, we have the induced magnetic pileup region. And this region has a long magnetic tail, and this magnetic tail is formed by the drip of the IMF lines. And this magnetic tail is also the main escape channel for our ions. And finally, we reach the ionosphere and the ionopoles. This part is located above the main atmosphere, and it is located on the top of the atmosphere. And this part of the region is formed mainly by the ionization of solar UV radiation. Okay, let's talk about our models. For planets observation, we all know that we do not have enough numbers of satellites to detect our planets. So three main kinds of models have been developed for many years to understand the solar wind interactions or provide some interpretation for the satellite data. First, we have the gas dynamic model, and we can call this type of model to be the particle model, because this model assumes that the ional pulse is the main obstacle to the solar wind flow. And the second, we have the hybrid model. We call it a hybrid model because it is a combination of the pure particle model and the MHD model. This type of model treat ions as particles, and they treat the electron as the magnetized flow. From my own view, I believe this type of model is quite reasonable because it can take the mass difference between different species into consideration. But this type of model requires a huge amount of computer capacity. Finally, the final type of model is our MHD model, which is our model. The MHD model treats our plasma as a magnetized fluid and can include the complete photochemical process. An MHD model can be divided into two kinds of models. The first type is a multi-species MHD model, or we can call it the single fluid MHD model. Because this type of model assumes that every ion species share the same velocity and temperature. And the second type is multi-fluid MHD model, which is now developed. This type of model assumes that every ion species has their own velocity and temperature. And this type of model solves a set of MHD equations separately for each species. Okay, now let me introduce the governing equations in our MHD model. Our models of the Navier-Stokes equations for four kinds of ion species that is represented by H+, O2+, and CO2+. And four kinds of species is enough to replicate or reproduce the whole structure of our induced magnetosphere. And then the Navier-Stokes include the continuity, momentum, and energy conservations. And the traditional Navier-Stokes equations are modified to incorporate the electromagnetic fields. Finally, the most important part in our model is the magnetic induction equation, because the magnetic induction equations in our model involves the terms of Hall effect and the electron thermal pressure gradient. So hard to work these two terms into our simulation. And in the continuity, momentum, and energy equations, we add the collision terms into these equations. Firstly, let me introduce the elastic collisions. The elastic collisions, we can imagine the billiards or snowballs hitting each other. And this, imagine this process before the hitting and after the hitting, the species or the properties of each particle or each ion species remain unchanged. But the direction and the velocity of each ion or each ball will change. So the momentum and the energy of each particle, we see that they are changed, but the species or the or the varieties of each ions remained conserved. And our model only considers the elastic collisions between ions and the neutral species. And the collisions between ions and ions or ions with electrons are neglected because we believe this collisions between these ion species will be the inelastic collisions. And for the inelastic collisions, our model considers three types of collisions, and these three types of collisions are represented by chemical reactions like photoionization, charge exchange, and recombination. And the inelastic collisions, this type of collision not only change the momentum and energy of the particles, they will also change the properties or the kinds of species of the ions. Okay, now we confirm the governing equations, and then we need the grid information to define the computational domains, and we need the Venus neutral atmosphere. And in terms of our grid, we design the grid, then the grid points are denser near the Venus surface, and the points become gradually sparser farther away from Venus. This arrangement helps us reduce the computational cost, and this design can save us a lot of time, just like shown on the picture below. As for the Venus neutral atmosphere, we choose two main and neutral species to represent the Venus atmosphere. That is CO2 and oxygen. And the distribution of CO2 and OX distribution, it was taken directly from Fox and Sons' work in 2001. And now we have the grid, we have the neutral atmosphere. The next step is to ionize the neutral species that we set. For the sunlight, we cannot just assume that the sunlight is the same everywhere. We cannot assume it's the same at every altitude or every SZA angles. So we use the Chapman function to calculate the photoionization production rates. And the parameters or numbers on the table was not the real solar radiation flux and Venus, because Venus do not have the satellite or equipment to detect these numbers. These numbers are got from Earth, and then we calculated the solar radiation flux on Venus by the distance between solar and Venus. Okay, this slide shows the overall workflow of our Hall Multi-Fluid MHD model. Firstly, our model will read our grid information, and they will read our initial parameters. And in each iteration, we update the boundary calculations, calculate the source terms, and we will solve the Navier-Stokes equations, and we will calculate the average velocity of each ions. After the structure of the induced magnetosphere becomes stable, we will get the parameters like speed, number density over different species, and with this results, we can solve the problems we are facing with. But this is not the strategy to deal with the model, because this process runs step by step. And now we have 960,000 grid points. One single case used to take me more than 1 month to finish. That was too long. If one case cost me over 1 month, maybe I should change another topic. So this is not the newest strategy to solve our model. Okay, this page is our newest strategy. We use parallel computing now, which lets the model to run different parts at the same time, and this can save us a lot of time. In the process of reading grid information, we divide the grid into many small parts, so the different processors on computer can work on different parts at the same time. And between different processors, we include a data transfer between different processes to keep everything consistent. I say to keep everything consistent means there's different processors, they can exchange their information on the boundary of each small part. Oh, the same case I said before, the old strategy will cost me over 1 month to finish. With the help of parallel computing, one single case only needs 1 week, 7 days or 10 days to finish. Okay, we have our model, and our model can run smoothly. Okay, before starting our research, the first thing we need to do is to make sure that our model is able to reproduce both the structures and the magnetic strengths correctly. So we choose a specific date and input the solar wind parameters into our MHD model. We input the solar wind number density, solar wind velocity, the magnetic field strength of IMF, and all of these parameters are detected by our Venus Express on June 1st, 2006. Then we run our model and we got our results. Then we compare the simulation results with the observations along the same orbital of Venus Express to check the model's accuracy. Here on the right 4 panels, we compare the X component, Y component, Z component of the magnetic field, and we compare the total strength of our magnetic field. From the comparison, we can see that our model has the capability, or our model can reproduce the positions of Bell-shock, MPB magnetic polar boundary, central tail and the strength of the total magnetic field can also match well. Okay, my research is to study the interaction process between the solar wind and Venus. So I used the average solar wind conditions from solar maximum and solar minimum in solar cycle 21 to reproduce the average structures of Venus-induced magnetosphere. I chose solar cycle 21 is just because we need to make a comparison with some earlier models. Okay, these two pictures show the structure of ionosphere and the subsolar point. In these 2 plots, we draw a vertical line and the subsolar point, and we show how the different ion species will change along the altitude. And from these 2 panels, we can see that below nearly 200 kilometers, the dominant species is O2+, because the CO2+ is unstable in the atmosphere. The CO2+ will react with the neutral oxygen to produce O2+ or O+. And above the 200 kilometers, the O plus replaces the O2 plus and the major ionospheric constitute. I did not posted a real situation on this picture, but this trend can match the real ionosphere structure detected by satellite or some other simulations. Yeah, as I mentioned before, the model is good at showing us the three-dimensional structure of Venus-induced magnetosphere. The figure on the left was got from more than 2 years of Venus Express data. It shows the average magnetic field strength and the structure of Venus-induced magnetosphere. The 4 pictures on the right was obtained from our simulations. I made slices on the XY plane and the XZ plane. The X plane picture is enlarged to show the piling up of the magnetic field. From the figure A and the figure B, we can see that the IMF layers pile up above the surface of Venus, and the layers also drift to the night side to form the magnetotail. And we can compare the figures between A and B or C and D. We can see that the bow shock was compressed in closer to Venus and solar minimum. And this figure shows the magnetic field topology around Venus. And these 3 pictures took from the solar maximum. In these 3 pictures, I extracted the several hundred field lines from the bottom of the model to show their overall shape and the structure. Understanding the magnetic field topology helps us to see how field lines will guide our ions to escape from Venus into the universe or into the space. The magnetic topology can be divided into 3 types. We have closed lines, we have open lines, and we have drift lines. And the proportion of these 3 lines can change depending on the different altitude above the Venus. In the panel C, the final panel, we can observe some closed magnetic field lines on the night side of the Venus. Yes, and our multi-fluid imaging model can calculate the number densities and the escape rate of different ions. And for H plus in our model is used to represent the solar wind. So the H plus is mainly concentrated along the bow shock because this is the place where the solar wind will be decelerated and compressed. And the H plus peak numbers are different between solar maximum and the solar minimum, just because the compress of the bow shock. As for planetary ions, in our simulation, O2 plus, O plus, and CO2 plus are used to represent the planetary ions. And these 3 types of ions primarily concentrated in the vicinity of the ionosphere and the magnetotail because they originated from the ionosphere and then they are picked up by the solar wind and escape from through the magnetotail. And we calculate these 3 ions escape rate, and every kind of species show a higher escape rate in solar minimum, which is mainly caused by the higher solar wind dynamic flow. This picture shows the ion velocity distribution in Venus, and The velocity distribution is shown in a three-dimensional space. And also we took the solar maximum as an example. And we took O plus as an example because it has the biggest number density about Venus. And the vectors on these three panels show the velocity distribution. And from these three pictures, we can see that the ions mainly picked up or catch by the solar wind from this side of Venus, and then they will be accelerated to a higher speed, and they can be accelerated nearly
Past.
okay, and then they can be accelerated to velocity or speed nearly solar wind speed. When I introduced our governing equations in our model, I mentioned that the Hall term and the initial pressure gradient term is the most important part in our MHD model. And next, I will examine how these two terms will affect our simulation results. Among all of these strict structures, we say that the bow shock is the first boundary that the solar wind will encounter. On these pictures, I showed the boundary, the bow shock is totally symmetric, but actually this bow shock or this boundary is not always symmetric. It has three main types of asymmetries. The bow shock has the magnetic north-south asymmetry, which is caused by the asymmetric mass loading. And usually, the bow shock on the north hemisphere will locate farther from Venus than the south part. And the second type of bow shock asymmetry is the equator to pole asymmetry. And this type of asymmetry is mainly caused by the propagation of magnetosonic wave. And usually the bow shock on the pole will locate farther from Venus than the pole's part. And the final type is the perpendicular parallel asymmetry, which is my research focus. And this type of symmetry will be affected by the angle between IMF and the bow shock normal direction. Okay, now let's talk about how the IMF angle can affect the Venus bow shock asymmetries. We know that due to the solar rotation, the IMF usually forms a spiral mode rather than a straight radial line. And why this type of asymmetry can occur? Firstly, we design an angle theta, and this theta is the angle between the IM direction and the bow shock normal direction. It should be noticed that this is a bow shock normal direction, not for some horizontal direction. And when the theta is less than 45 degrees, we can classify this part of bow shock as quasi-parallel bow shock. And this type of bow shock is closer to Venus. And when the theta Bn is greater than 45 degrees, and this type of bow shock can be classified as quasi-perpendicular bow shock. And this type of bow shock is usually farther away from Venus. And how these angles will affect the perpendicular parallel symmetry. Because the bow shock forms by the speeding of the fast magnetosonic waves when the IMF is perpendicular to the bow shock. The theta Bn can get its maximum, and the theta Bn gets its maximum, then the cosine theta Bn will equals to 0. And as a result, the bow shock will form farther away from Venus. And on the contrary, when the IMF is parallel to the bow shock, we will get a minimum value of theta, and then we will get the maximum value of cosine theta. And as a result, the bow shock will form closer to the Venus. Okay, now I made 3 cases to simulate different situations. I simulated IMF angles under 50 degree, 36 degree, and 90 degree. I do not simulate it under 0 degree because the 0 degree is very difficult to simulate. It's too special. And the 36 degree is the average degree in solar cycle 21. And the 19 degree is also a special, also special scenario. And under 19.6 degree, the IMF will totally perpendicular to the solar wind. And this is what our models are good at. We can changing only one upcoming parameters in solar wind. And I divided the bow shock into quasi-parallel bow shock and quasi-perpendicular bow shock. And then panels A and panels B, the quasi-Q-perp bow shock is farther away from Venus, and the Q-peri bow shock is closer from Venus. This can prove that our model replicates the real situation on Venus. As for the 90-degree case, it is very special between there is no asymmetries observed, which is also can agree well with what the satellite detected. Because the dataset bow shock all of the dataset bow shock can be classified as a Q-perp bow shock. And that's the reason why the asymmetry disappears on this 90-degree case. Okay, because the bow shock is the main obstacle, or we can say it's an obstacle to the incoming solar wind. So let's see how the solar wind interact with the bow shock. And I introduced before that we use H plus to represent the solar wind flow. And because the solar wind flow will be decelerated by bow shock, so we can see that the H plus ions are mainly concentrated along the bow shock and show some asymmetry along this bow shock. And for 90-degree case, just like the magnetic field distribution, the symmetry of ion species or ion density or the velocity disappears. Okay, now let's talk about the electric field and how it will help us understand the bow shock symmetry. According to the Faraday law of introduction, we know that changes in the magnetic field will affect the distribution of the electric field. And in our model, we use the generalized Ohm's law. And in the generalized Ohm's law, the electric field can be divided into 3 parts. They can be divided into motional electric field or electric field and the ambipolar polar electric field. In the first 3 panels, we show the motional electric field distribution on the XY plane. And of course, this type of electric field takes the most part of the induced magnetosphere. But comparing with the next 2 electric fields, this type of electric field has no big enough magnitude along the bow shock. So we cannot say that this motional electric field can determine the position of bow shock. And then in the next 3 panels, we show the distribution of ambipolar electric field. The ambipolar electric field has enough strong magnitude along the bow shock, but its strength does not show a very clear symmetry regarding the different bow shocks. And finally, we have the Hall electric field. The Hall electric field is expressed as J cross B. And this type of electrical field in the Q-part shock is stronger compared than that on the variable shock. Okay, that's just the XY plane. Then we will to see which electrical field matters most for the symmetry. We look at the values along two lines. The one line is cut through the positive 45 degree, and the green line cuts through the minus 45 degree, and the orange line goes through the Q parabol shock, and the blue line will go through the Q perp side ball shock. On the Q parabol shock, we can see that at the position of ball shock, the whole electric field is not strong enough. So the solar wind will compress the ball shock into a lower altitude. And then the ambipolar electric field, which comes from the electron pressure, will get stronger, and it will become stronger enough to stop the solar wind and acts as a primary barrier. And on the contrary, on the Q parabol shock, a stronger Hall electric field can develop, and then the Hall electric field and the ambipolar electric field can work together to stop the solar wind. Okay, we say that the Hall electric field is the main function then to stop the solar wind. Then I will explain why the Hall field is stronger and the quasi-perpendicular ball shock. According to the Apis law, we know that the current density depends the type of the magnetic field. On the Q parabol shock, the IMF is nearly perpendicular to the ball shock normal direction, which means the magnetic field lines are strongly distorted and bend sharply when the IMF enters the ball shock. And the strong distortion and bend will result a sharp change in the magnetic field. And the sharp change in magnetic field will lead to a stronger current density and a stronger Hall electric field. On the contrary, on Q parabol shock, the IMF is nearly allied with the ball shock normal direction, so the field lines won't bend too much and won't get too much change along this direction. So we will get a weaker curl of the field lines, and as a result, there won't be a strong current density and the Hall electric field. In the previous cases, I introduced the results under the average solar wind conditions. Now I want to introduce the simulation under some solar wind events. Let's take the ICME event as an example. The ICME event, its total name is the interplanetary corona mass ejection. And this event is a large eruption of plasma and magnetic field from the solar. It can bring solar wind with higher number density, temperature, velocity, and the IMF. We simulated a special day on the November 5th, 2011. We took the solar wind parameters from the Venus Express and we input the solar wind condition before the event into our model. And then our model runs to a stable situation. And then we give our model the event solar wind situation condition. And then we can see how the Venus-induced magnetosphere will react to the changing solar wind conditions. Firstly, before this event, we got a steady state before this event arrival. And after that, we give our model the event solar wind conditions. That interaction process can be changed. And after that, we got a new steady state after this ICME event. we can see that the main changes in the changed, and the strength of the induced magnetosphere has gained, dropped.
45.
Oh, that's good.
Thank you very much, Nihan, for this interesting presentation. And now opening is for questions, and Helmut has his hand on.
Maybe you can go back to the slide with the escape rates.
Breeze.
Yeah, you had the slide where the oxygen ion escape and.
Oh, yes, this all lines.
It's here, yeah.
Yeah. Hold on.
Well, there was, it was there, this, yeah. Yes, yeah. So did you compare the rates with the observations of the Aspera instrument on board on Venus Express? Because it seemed to me that if I take oxygen, it's quite high. So it may be a factor of 10 higher than what they analyzed or observed over 8 years.
8 years.
Yeah, it's around, I think the average escape rate is in the orders, what they found in the orders of around 3 times, 2 times, whatever, 10 to 24. So it seemed to me that these escape rates are quite high in their model.
You mean the escape rate is a little higher?
They are higher, factor 10 than what the Aspera instrument on Venus Express observed. So, yeah.
1 to 5 times 10 to 25 is what Venus Express observed for oxygen.
Okay.
So I think it's for oxygen, and I mean, if it didn't take a look on it, then I would suggest you have to compare it, because I would be surprised if Venus Express may have overseen over all the time, because the factor 10 is quite high.
Actually,
If that would be, if these values are more or less, if they would be accurate, then Venus Express would have overseen the main ion escape channel. It's only I see. So so it would be interesting. And then another thing is more connected to the model. Would it be easy for you? I mean, easy. If we would, for instance, provide, you have now as an oxygen and CO2 as the neutral atmosphere, but there would be also a possibility to study maybe carbon atoms. Yes, they may be produced superthermal. You will have in the exosphere high up a carbon component, which is related to CO2, of course, when it's dissociated, and also oxygen. So hot carbon, hot oxygen, hot hydrogen, and hot deuterium. So we could provide the number density as a function of altitude, as an input, additional input, for instance. And then we would be interested what is the ion escape of this. But first, of course, we have to take a look on these values.
okay.
If they have to, we have to find out why they disagree with Venus Express.
But I made a
My suggestion. But
okay. I understand, but the simulations are made under the PVO numbers.
yeah, I don't know. Yeah, but also for PVO, I think they
A little higher.
may be higher.
Okay.
But we have to check. It's interesting for me to check it also. But if in case generally it's not a problem to include additional neutral gas profiles. I mean, could you calculate this again, for instance, and if you have an input of neutral carbon or deuterium, you get out the carbon ion escape and deuterium ion escape. Then we can speak afterwards.
Yeah.
Okay, first of all, thank you. That was a very nice presentation. I found it extremely clear as someone who does not work every day with this, so congratulations for that. I really loved it. I have a similar question with escape rates. This model, do you also have an application for Earth?
For Earth,
For Earth.
no, we do not have for Earth.
Okay, because I mean, one of the things that piqued my interest in this field in the last years that there was actually a paper by Herbert Brunel, 2018, that has also discussed later that magnetic fields do not necessarily shield you from atmospheric escape, right? Because the problem is that when you have magnetic fields, you also funnel electrons to the polar regions, and that can lead to increased polar outflow. And there, I would be interested to see with this kind of model if you basically can confirm this, or if basically you say that there are other mechanisms that actually prevent this polar outflow, because this also has been discussed that the polar outflow can actually be prevented by some other mechanism that actually gives the atmosphere back and basically then provides the shielding. So this question of is magnetic field actually good for atmospheric escape or not seems to be debatable, and I would be interested to see, or maybe do you have an opinion on this? Is magnetic, because here it looks like the escape rates are high but pretty comparable to Earth. Do you think magnetic fields are really necessary for atmospheric loss?
Actually, I never considered to apply it to Earth.
Okay.
Yes, I thought Earth has so many satellites is a model used.
Yeah, I don't know. I mean, it's like maybe Helmut is more up to date with the debate, but that was also, so there are people that are considering the roles of magnetic fields in the shielding of a planetary atmosphere, and it appears to be not as clear as people made it out to be for a very long time.
Okay.
Seiji, then Daniel.
Could you go back to the original basic equation system? And I understand that you solve many ion species separately, so that's a multi-fluid. And in that case, how do you solve electrons? Is electrons independent fluid, or is electrons some virtual fluid, charge neutralizing fluid?
Okay, actually, there is no real electrons in imagery model. Electrons are treated as the background because the imagery model follows the theory of neutrality. It means in the calculation domains, the total number of electrons will be equal to the total numbers of ions. So it's treated as the background.
Is that the charge neutralizing fluid?
Yes.
Thank you.
Daniel?
Yeah, thank you for a nice talk. I was wondering about the boundary difference in the model. So how do you treat like these outer boundaries? So you showed the mesh grid in some slide.
Boundary.
Yes, so you showed in one slide the mesh grid of the simulation. Which slide it was? This one, yeah. And I was wondering, how do you treat kind of the boundary, the outer boundary of the simulation, and also the planet itself? How do you treat the surface of Venus in your equations? So maybe you can talk a bit about how you solve equations maybe inside the planet, or do you leave it out? And also on the outside boundary. So I guess you have solar wind inflow from one side, but that gets complicated because you have a complicated geometry of the mesh grid.
Okay, from the outer. The outer is totally solar wind. And this and that number density will reaches to nearly zero at a comparatively low altitude because it's a straight line. So actually the boundary is very low. This is for the atmosphere components. I wish I explained clear.
Do you also see like any numerical issues with the magnetic field at the boundaries, or do you have any suppression methods for how the IMF, for instance? Do you see any draping or any numerical issues at the boundaries?
Boundaries, which boundary? MPB or
Outer boundaries.
outer boundaries?
Yeah.
You mean the total region?
Yeah.
Oh no, there's no and the side of solar, there's no apparent seminar or phenomena because it's all the steady solar wind or stable solar wind. And the other side, the magnetic tail side, there is some particles, but the particle number density is relatively low. So we do not discuss the very far tail region. We mainly discussed the tail region within 3 to 5 or 6 radius of Venus.
A nice talk. When you compare the magnetic field from model and data, the largest differences are for the BX component. This is one comparison, but towards the end of your talk, there is another comparison between model and measured magnetic field. Not here. This is the total magnetic field, and this is coming from the large error in BX. Because the other, yeah. So in the total magnetic field, you have these large deviations because of BX.
Yes.
But please go to the end of your talk when you are making another comparison between model and magnetic field. To the end of the talk.
I see me. Yeah.
Oh, okay. Oh, here.
No, this one. Okay, so now if we look again to the BX component of the magnetic field, it is not just a large difference, but in one case you have a plus and another case you have minus. So one BX is showing towards the sun and the other one is from the sun. So it's completely not just large error, but I do not know why this appears in your model.
Because this is a very awkward situation. Because we got the IMF from magnetometer, of course, and the solar wind, and we need the solar wind velocity and the particle numbers. But the S-power has different resolution. We cannot get the total value from the solar wind. So these simulations are run only under the real IMF parameters, not the real solar wind numbers. So the BX usually will show some discrepancies and the position of magnetic tail central. That's really true. You are so careful. And we don't know how to solve this because we cannot get the accurate parameter from the solar wind.
I'm a bit lost. So on one hand, you mentioned that you take into consideration the reactions of charge exchange, ionization, recombination. So on the other hand, I don't see neutrals in your equations. So if, for example, you show us the generalized Ohm's law, which you consider, there is no neutrals, yes, here. So the ambipolar term, which is in fact, you call it gradient term, it will vanish anyway when you take the rotor of electric field. On the other hand, the ambipolar term in the generalized Ohm's equation is slightly different. It is G cross B, dependent on the ion neutral collisions, but we do not see neutrals in your model. How do you resolve this problem? Neutral particles.
Pardon, you mean we should include neutrals in the generalized equation?
So if it is a partially ionized plasma, then it has to contain also the neutral related term. This is well known.
Okay.
This term is normally used ambipolar term, not one proportional to the pressure, electron pressure gradient. This term doesn't play a role at all, because if you substitute this electric field into your Faraday law, rotor of the gradient will be 0. It vanish automatically.
Okay, I didn't take that into consideration for now. Thank you for your suggestion. Okay.
So maybe it's better to rephrase it to electron inertia or electron thermal inertia or something like that. But I also agree that ambipolar, the term ambipolar is a little bit misleading in this context. But it's just a matter of phrase.
Yeah, it's not only the definition, so it's a part of the story. So it's not ambipolar term,
No.
and this will not contribute the induction question at all, because operation of rotor will cancel it.
Yes.
The ambipolar term in the generalized Ohm's law is V cross B cross B, which comes due to interaction of ions and neutrals, ion-neutral collision. It is completely missing here. But this term will also contribute to the induction equation. Technical aspect. The philosophical aspect, she discusses the ionization and recombination. So the neutrals are naturally supposed in the system, but they are absent in the equations. And this is my problem.
Any more questions? Well, I think there's a couple of collaborations that can be done here also. I think Helmut is very interested in looking at this. And we thank you once more for this very nice presentation. And we are hoping to benefit of your presence here for the last few months that you've learned. Thank you very much.